Okay, let's try to get this last one done again. Sorry about that, kind of crashed on the um, last attempt. So this is labeled as a motion problem. We have a boat that is traveling 36 miles up a river. It takes it 3 hours to do that. Returning downstream, the boat takes 2 hours. And the question is, what is the boat's rate in still water and what is the rate of the river's current? Okay, the thing about boats is they certainly, if the current will add to their speed, if they're going with the current, it will take away from it if they're going against it. But it does ask for the rate in still water, and it asks for the rate of the current. So those are the two things we want to know. We don't know them, we're going to make those our variables. So we'll make x the rate in still water, and we will make y the rate of the current. The other thing that we're going to make use of along the way here is the concept of rate times time equals distance. For example, if we're driving 60 miles an hour for 3 hours, we've gone 180 miles. That's the idea there. Okay. So we get two directions that we went. It's the same distance either way. So the one upriver, if they're traveling up the river, then the river is slowing us down. So our rate in that case is going to be the speed of the boat in still water, and we're going to subtract from that the rate of the current. Okay, hopefully the boat's speed in still water is faster than the current, otherwise we're not going anywhere. Times the time, we know that that took 3 hours going that direction. And the distance that got us is 36 miles. So there is, if I was labeling this, I would say this is our upstream equation, where we're fighting the current. We also have a downstream equation where the speed of the boat is working together with the current, so we can go much faster, and we can see that much faster accounted for just 2 hours that it took to do that. And to cover the same 36 miles, this is our downstream equation. Okay. Now, things that we could do on this, if we distributed the 3 and the 2 through here, we'd be able to make some adjustments. But also, since that's primarily multiplication over there, I'm going to take that top equation and divide both sides by 3, and that's just going to tell me that the x minus the y is equal to 36 divided by 3, which is 12. Okay, so that's from that equation, dividing them both by 3. And if I do a similar thing to the second equation where I am dividing both sides by 2, in that case I'm going to get an x plus y is equal to 18. And this is set up already that all I have to do is add these two things together, and the y's will go away. I'll get a 2x is equal to 30. So x is 15. X was the rate in still water. This is 15 miles per hour. And I can use one of my other equations then, like if I borrow this one, now that I know that the x is 15, this says 15 minus whatever y is has to equal 12. Okay, well I can see the thing that I subtract from 15 to get 12 is 3, so the current is 3 miles per hour in the river. And so that's how we do a motion type of problem. That's now examples of 4 different types of problems that set up as systems of equations. So you have a number of examples there to look at.